Alright, in those 20 minutes you should have completed the linear versus exponential worksheet. If you have not finished that worksheet, then it needs to be completed for homework tonight. We're going to go ahead and move on to the next section of notes, and that section is going to be over exponential growth and decay. So we want to be able to solve problems involving exponential growth or decay functions. We're going to first talk about growth. When we talk about growth, it means to get bigger. So we're looking for a function that's going to make something bigger. The paper folding activity yesterday is a great example of this. Remember, as the more we folded, the quicker and quicker it accelerated to have more and more sections. Remember, by the end, we had that great big long number times 10 to the 30th, which gave us a huge number for 100 folds. So we're going to have a basic equation we use for exponential growth. And it's going to look like this. Y equals A, parentheses, 1 plus r, parentheses, raised to the t power. A is going to be our start value. It's going to be whatever amount we start with. R is going to be a percent increase. The problem will say it will increase by 10% or it will increase by 5%. To plug it into our formula, though, we need to change that percentage into a decimal. So, for example, if it said 15%, we would need to move the decimal 2 places over, and that would become 0.15, and that would be our R. Now, a little bit tricky vocabulary here. If we're talking about growth rate, our growth rate, if it asks for that, is going to be our R. It's going to be the part inside the parentheses. If it asks for our growth factor, it's going to be 1 plus R. So that's something that's going to be important for you guys to tell apart. It sounds very similar, but on the milestone, they'll catch you with that. It's two different things. And then finally, T is going to be the number of time periods. So if something goes per year, it would be however many years you have. If it were per month, it would be however many months you have. So let's jump into an example. If you look on the next slide, we have a colony of 10,000 ants. A lot of ants. And it increases by 15% a month. How many ants will be in the colony after year 1? So just a reminder, our exponential growth formula is y equals a, parentheses, 1 plus r raised to the t power. So I'm going to highlight our important information here. So that 10,000 is our starting amount. So we are going to plug 10,000 in for our a. Everything else is going to stay the same. We're going to have the parentheses and the 1. That parentheses 1 is automatic every time. Plus, it grows at a 15% growth rate. So 15% as a decimal, we move the decimal over 2. It's going to be 0.15. 0.15. And it's raised to the t. In this case, it was 15% in a month, and we're looking at the colony after 1 year. We think about how many months are in a year. That's 12. So t is going to be 12. So now we can simplify this. Y equals 10,000 times 1.15 when we add those together to the 12th. And at this point, you're going to want to use your calculator. All right, so if we type into our calculator, let's see if I can get that to show up a little better here. Okay, we're going to type in 10,000 and then parentheses 1.15, and it's going to be the same whether you're using the blue calculators or the yellow calculators. Raised, remember we hit that caret, and for the yellow calculators it's going to make it go up into the little box. If you have the blue calculator, then you'll just keep typing. And our exponent in this case is 12. So we're going to hit enter. And if I move it away from the glare, you're going to see that that is 53,502. Now, it gives a decimal, we can see that. But we got to think about the context of this problem. Does it make sense for an ant colony to have just half an ant laying around? Maybe if it's dead, but they aren't going to have a living ant just sitting there halfway born. So we're just going to go ahead and round to the lowest whole number because that half an ant isn't quite enough to make another whole ant. So we're going to leave it as 53,502 ants. Make sure you have that problem down, and we'll move on to the next problem. A baby weighing 7 pounds at birth, so I'm going to highlight my important facts here, increases in weight 11% a month for the first 12 months, and it wants to know how much will the baby weigh after a year. So we're going to set this up again. Our initial amount is going to be 7 pounds. We're going to have 1 plus. This time it's 11%. So if we move that to be a decimal, it's going to be 0.11. And it's for the first 12 months, and the baby will weigh after 1 year. It's per month, so that's going to be a 12 for our t. 1 plus 0.11 is going to be 1.11 raised to the 12. And if we type that into our calculator, we're going to get that this is going to be 24.49 pounds. In this case, it makes sense that you can have part of a pound. So I'm just going to round the 2 decimal places. So that's 24.49 pounds. Remember, LBS is our abbreviation for pounds. All right. I want you guys to try the next one. Before you pause the video, I'm just going to give you a little help, a little hint. 7 1/4% is the same thing as 7.25%. All right? I'm going to ask that the substitute pause the video and let you guys try this on your own. All right, so hopefully you guys got this. Let's go ahead and look at what this would mean. Our starting amount was $1,500. Our rate was 7.25%, so if we move the decimal 2 places, we're going to have to put a 0 in there. So it would be 0.0725. I hope you guys all caught that once I give you guys the hint. And this is compounded annually. Annually, if you remember, means once a year. All right, and it's 1 time a year for 8 years. So our t is going to be 8. Once we plug that in, we're going to find, and remember our answer is in money, it's going to be $2,625.84. The reason we round to 2 decimal places in this case, we're talking about money. Money always goes to 2 decimal places. Show of hands, how many people got this right? Good. All right. Sometimes they will try and trick you up the way that a problem is worded. If we are talking about percent increase or growth factor, these problems might be worded a little bit differently. So in this case, we have a few things that are worded all the same way, or all different ways, but all have the same answer. So if we read the first problem, a population of 10 hamsters will triple every year for 4 years. What will the population be after 4 years? So there are 2 ways we can look at this. One is percent increase. Population is 200% more than last year. All right, the reason this works like this, all right, remember our initial was 10. We start out with a 1, and then we add our r. In this case, our r would be 200%. But 200% as a decimal would be a whole number 2. So this is like adding the 100% that we started with plus the 200% that made the population increase, and we want it after 4 years. So if we simplify, it's a is going to be 10 times 1 plus 2. We're going to raise it to the 4th power. All right. Remember, growth factor we said was 1 plus r. So if it gives us a growth factor where the population is 3 times as much as last year, that inside the parentheses, the 1 plus r, is going to be 3. So we still have the same initial amount, we still have the same time, but it's going to be 10 times 3 raised to the 4th. Notice when we simplify over here, it's going to be the same thing. So 2 different ways to look at the same problem. Right. Looking now, we want to look at exponential decay. If growth means it's increasing, decay means it's going to decrease. This is a function that's going to go down as you go. Alright, the formula is going to look almost exactly the same. The biggest difference is what's right there in the middle. Remember, on exponential growth, we had a plus sign. If you think increase, adding means to increase. On decay, where we're decreasing, we have a subtraction sign. So that is the only difference. A is still going to be our start rate. R will still be our growth rate. This time, though, our growth factor will be 1 minus r instead of 1 plus r, and t is still going to be the number of time periods. So, if we have a radioactive material that decays at 10% per year, we want to know how much of the 12-pound material will be left after 20 years. So, if we remember our formula, it was y equals a times 1 minus r to the t. A was our starting amount. In this case, it would be 12 pounds, times parentheses 1 minus, and again, we have to change this percentage to a decimal. So 10% as a decimal would be 0.1 raised to the t. In this case, our time was 20 years. So we simplify 12 times 1 minus 0.1 to the 20th. When we simplify that, is going to be 0.9. Notice when we simplify, that number is going to become less than 1. If it's growth, that number inside will be 1 or greater. So we still have to the 20th. Now when we type that into our calculator, we type it in exactly the same way. We're going to find that it comes out to be 1.46 pounds. I want you guys to try this next one. The substitute will pause the video and give you guys 2 or 3 minutes to finish this, and then they'll press play so that you can check your answer. Alright, so hopefully you have this problem worked now. So our initial starting amount was $24,500 times parentheses 1 minus, it was 18%, and depreciate. Anytime you see depreciate, that means go down in value. A car, as soon as you buy it and take it off the lot, it starts depreciating in value. It's worth less and less. A lot of times real estate can depreciate as well. But our rate was 18%, so as a decimal, that was 0.18. And we're looking at the first 6 years. So, we type that into our calculator, and we're going to find the amount that it's worth at the end as $7,448.16. Now, remember, this was talking about money, so we want to make sure we include our units. All right, one more time, just so we can see the difference between growth and decay. We'll do 2 side by side with it has the same percentage. So we have $100. One's going to grow at 10%. One's going to decay at 10%. We already have the equations written. When we simplify, notice on the inside that this is going to be bigger than 1. For our decay, it's going to be less than 1 if I don't mess up my writing here, it would be 0.9 to the x. Now in both cases, we're looking at 5 years. So I'm going to go ahead and plug in 5 for our x or our t, depending on how you're looking at it. I forgot that initial 100 there. So it's 100 times 0.9 to the fifth. You're going to find out that this is going to be $161.05, and this will be $59.05 once you type that into your calculators. So as you can see, our growth factor, we ended up with more money, but when we decayed or depreciated, we ended up with less money. One more thing before we move on. I want you guys to label whether these are growth or decay. I'm going to have the substitute pause the video. I want you to answer and identify each of these 6 as growth or decay. And then the substitute will press play again, and you guys will finish. We'll finish by checking. All right. So hopefully you guys have given this a shot, and you should have an answer as to what each of these are by now. If we are looking at these, we can say that we have growth, 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 decay, decay, growth. And the way we can tell is by looking at that number inside the parentheses. Even if we don't see the plus or minus sign, we know that 1.04 is greater than 1, therefore it's growth. We know that we're adding there, so it's growth. We know that 2 is bigger than 1, so it's growth. Decay, 0.97, that means we would have had to subtract something from 1, so we know it is decay. On 5, we can see the subtraction straight out there and know that it's going to be decay as well. And finally, 6 is going to be growth because that 4 is greater than 1. So hopefully you can tell the difference between growth and decay now. There was one more example problem in your notes, but this video is reaching its cutoff, so I'm going to go ahead and skip this one for now. Maybe we'll come back to it when I'm back in class. Your sub will now hand out a sheet on exponential growth and decay. I would like you guys to go ahead and complete this. If you guys finish before the end of the bell, there's one more video for you guys to watch. It's going to be on compound growth when we start talking about money, compound interest. And if you do not finish the exponential growth worksheet in class, then you need to complete that as homework. So at this point, the 2 things you have, if you have not finished them for homework, is the linear versus exponential worksheet that you handed out in between the 2 videos. And now this exponential growth and decay video that you guys have.